Okay, Travis, you can continue your second talk.
Okay.
Okay. Yeah.
Okay. So, I basically just pick up where I left off last time. I didn't actually prepare slides for two separate talks. I just did one long talk and figured I'd stop wherever it was convenient with the timing. Where I left off, we were talking about how mutation changes your lattice structure, or acts on basically your seed data or your blow directions by some piecewise linear map. So this motivates U-trop, which is basically a modification. Instead of working with the status n, U-trop is something very closely related you can work with that doesn't change when you mutate. It's actually canonical. So U-trop will be an integral linear manifold with a singularity at the origin, and it's canonically associated to U. So that's, let me mention, this stuff you can do in any dimension, like log Flabiaus in any dimension, cluster varieties in any dimension. It's special to dimension 2 that this only depends on U. In higher dimensions, this ends up depending on the boundary also. So what is an integral linear manifold? Well, it's a topological manifold where your transition functions live in SO2Z. So as I said, there's a singularity at 0. So we have to look at the complement of that, U-trop minus 0, or that U0 trop. And on there, we have charts to R2, such that the transition functions between charts live in SO2Z. You could also say SP2Z, it preserves that some skew symmetric pairing we had. And one nice property of this is you could talk about U trop of Z. There are well-defined integer points in U trop. So you just take psi inverse of Z squared. So you're living in R2, you can take Z2, and you can take the preimage of that lattice. You can do that for each psi, and transition functions will preserve that lattice because they lie in SO2Z. So you get some well-defined integer points in U trop. Now, as a set, U trop is the same as just this n sub r, so the lattice n tensored with r. So remember that's isomorphic to r squared, because n was z squared. So as a set, U trop just looks like the plane, the real plane, but the integral linear structure will be different. So here's how we can put the right integral linear structure on n tensor r. We can pick some minimal model, some y comma d, which compactifies U. So some Looijenga pair y comma d, and that's just for convenience. Assume that there are at least 3 rays. You can get by without that though. U is our interior. I'm going to let row 1 through row s be the rays, corresponding to these divisors. I'll assume that they're cyclically ordered counterclockwise. So yeah, these are the rays corresponding to these divisors. Let's let Ni be the primitive generator for row I. That's that sigma sub I minus 1 to I be the cone bounded by these 2 rays, row I minus 1 and row I. So on each of these cones, the U trop will look the same as n sub r. Like they're set theoretically the same, and the integral linear structure is the same. So what we have to do is say how do you understand the integral linear structure across rays, across the rays between cones? So what we do is we say that if you take 2 adjacent cones and you look at their union, we just need to say, for each such pair, what is the integral linear structure on that union? And that will tell you what happens across the ray. And we just specify that the integral linear structure should make it so that this is true. Such that, so remember this was this equation we had before, that in general for a for toric surface, this should hold. This equality should hold. So we take that thing that we know holds for toric surfaces, and we just we build this integral linear manifold for any Looijenga pair, such that that same equality is satisfied. And the same equality determined by the intersection, self-intersection numbers of the boundary divisors. So let's look at an example of this. So let's consider we take P2 with 3 lines, so the toric P2, and let's do 2 non-toric blowups on each of the boundary divisors. So here's my P2. I'm doing 2 non-toric blowups on each of these. And I talked about this example before. This is the cubic surface going up 6 points in P2. So a line in P2 has self-intersection number 1. We blow up 2 points on it. So now it has self-intersection number -1, which blow up decreases that self-intersection number by 1. So di squared is equal to -1 for each I. So this equation that we had, that becomes n sub I -1 minus n sub I plus n sub I plus 1 is equal to 0 for each I, with these i's being cyclically labeled. So I could also write this as n sub I is equal to ni minus 1 plus n sub I plus 1. And we can use this to start drawing U trop. So what I'm actually going to draw here, or what's actually already drawn here, is what's called the developing map. So the developing map is basically you take the universal cover of U trop minus the origin. So this kind of infinite spiral. And then we will define an integral linear immersion of this into R2 minus the origin. So you basically, it's like you take some point in U trop 0 and say where that point, say where that maps in R2, so some point where that maps to. And then just as you move around in U trop from there, that corresponds to moving around in R2. And we're just specifying where things are mapping as you move around in this universal cover. So in other words, we say, we can just say maybe that, say that N1 points this way. Let's say N1 is the direction 1, 0. Up to isomorphism, we can choose N1 and N2. You can always choose N1 and N2 to be the directions 1, 0 and 0, 1. And then N3, N3 is determined by this equation, out of these equations. And so N3 should satisfy N3 plus N1 equals N2. So that tells you that N3 should be the vector -1, 1. So that when you add it to N1, you get N2. And then if you were to keep going, applying the same equation and say, where does N1 go, or where does the next vector go, you would get that N1 goes over here. Maybe I'll call it N1 prime this time. So that way, this vector plus this one add up to this one. Then you can keep going and get N2 prime, and then N3 prime. And then you could even keep going, and the next copy of N1 would be the same as the first copy. The next copy of N2 would be the same as the first copy. So we can keep going around like that.
What do you record the order?
Sorry?
I mean, how do you record the order? You should do it, or?
So I've just kind of assumed that I've chosen some cyclic ordering on these so that the rays go counterclockwise. So I haven't been writing it, but I'm kind of always assuming that my labeling is counterclockwise cyclically ordered. This cone is basically just another copy of this cone. It's just the next sheet up on this universal cover. And then if you want to get from the universal cover back to utrop, you just need, you apply some linear map that identifies this cone with this one. You need a linear map that takes n1 prime, n2 prime to n1 and n2. And that map gives you the monodromy. It tells you how you relate one copy of utrop to the next copy, to the next sheet in this universal cover. And from that, you see there's some monodromy around the origin in utrop. And you can think of it as, if in this cone, if you start with the vector parallel to n1, tangent vector parallel to n1, and you translate that over to here, or translate that to down here, well, now this direction is negative n1. I should say negative n1 prime. On this sheet of utrop, it looks like it's parallel to negative n1 instead of parallel to n1. So the monodromy here is negative the identity matrix. Negative the identity, because every vector after you go up one sheet on the universal cover looks like it's pointing the opposite direction. So the monodromy mu, I'll talk about more on the next slide. In this case, looks like negative the identity map. So, yes. So in general, we always get some, or you're right, we always get some monodromy around the origin in utrop, except in the Tor cases, there's no monodromy, or it's trivial. So yes, the monodromy is trivial in the Tor cases. We just saw that it's negative the identity for the cubic surface. In general, each time you blow up a point, say you blow up a point on boundary divisor dv, that will add something to your monodromy. Basically, it adds a focus-focus singularity. So if you choose v to correspond to the direction 1, 0, this will contribute this matrix to your monodromy, 1, -1, 0, 1. And then if you have a bunch of VIs, assume that they're cyclically labeled counterclockwise, then as you go around utrop, you'll hit the rays generated by these. And each time you hit one of those rays, you apply the corresponding monodromy from that focus-focus singularity. So you basically apply this matrix, but in a different, you have to express it in the right basis. So instead of v being 1, 0, it'll be whatever vector. And if vi is the vector ai bi, then you can figure out the change of basis formula applied to this gives you this matrix. And so multiplying a bunch of matrices of this form gives you the monodromy. Or you can get the monodromy by doing this developing map construction and looking for the map that identifies the cone from the first copy of utrop with the cone from the next sheet. Now, I want to mention this because I believe I probably saw a bit about this in the talk before mine. You think you should
Unfortunately, they didn't. Sorry.
All right, well, you should see some stuff about this in other talks later on then. I think Yushen then is giving a talk next week on special Lagrangian fibrations of Looijenga pairs, I think. So maybe that'll make contact here. If not, I think this is worth mentioning anyway. So you should think of utrop, at least heuristically, as being the base for a special Lagrangian fibration of U, the base of an SYZ fibration. So you can think of utrop as being the base, or maybe kind of a dual version I might call vtrop. You can view vtrop as being identified with m sub r instead of n sub r. And then the monodromy would be the transpose of mu. And with matrix in SO2Z, the transpose is the same as rotating your basis by 90 degrees. So it's an isomorphic linear manifold, just rotating things. So that now, right, remember for a toric variety, if you have an ample divisor supported on the boundary, that determines a polytope. So it gives us a polytope. And you have a Lagrangian fibration of your algebraic torus over the interior of the polytope. And you have a torus fibration of the full toric variety over the polytope with lower dimensional tori over the boundary. So we have a Lagrangian fibration. You can make it a special Lagrangian fibration over this polytope. And Margaret Symington showed around 2003 that when you do a non-toric blowup at some boundary point here, and this predates Grossack and Keel by about a decade, she found if you have a Lagrangian fibration over a polytope like this, and you want to do some symplectic blowup of a point on, say, this boundary divisor, you can view that as cutting out a triangle, and you glue these two edges of the triangle, and then you do some corresponding surgery on your Lagrangian fibration. You end up, so over most points here, you have a torus fiber. Over this point, over this point, you'll get a pinched torus. And if you do a bunch of toric blowups, you can just view that as doing the surgery for a bunch of triangles. You can also do this on other components, for blowups on other boundary divisors. And then all of these focus singularities, sorry, each one of these gives you a focus singularity from the monodromy around that. That's the monodromy of the fundamental group of these tori, or the homology of these tori living up above. And the monodromy from going around all of these singularities will be the same as our monodromy. I don't know if it's exactly mu transpose or mu, but up to something that's not a big deal, you get the same as our monodromy. So that gives you that there's a Lagrangian fibration over U-trop, or maybe the dual to it or something, or some polytope in there. Special Lagrangian fibration is harder, but from what I understand, there's a more recent paper by Chung, Evans, Hong, and Lin, which shows that you do get special Lagrangian fibrations, I assume over the same base or something close to this base, maybe with the singularities deformed like this. And I think Yushen will talk about related work next week. I don't know if it's this one, but don't know the details of how that works. But yeah, there are now special Lagrangian fibrations for these things. So this is more kind of motivation. I'm not really going to use this for stuff later, but I think it's good to know about. So right, so I mentioned we have this monodromy in U-trop. So because of this monodromy, when you draw a straight line in U-trop, you can actually have a straight line which intersects itself. So a line in U-trop might wrap around the origin and come back the way that it came from, or self-intersect. So we have a singular point at the origin. We have a straight line that looks something like this. Or we saw with the cubic surface case that a straight line comes in from one direction and goes back to infinity in that same direction. So that, maybe go back to that slide. Too much drawn here. So if you take a straight line here, just extend it that way, if you project this down to just U-trop instead of this universal cover, it will look like it's gone around the origin and wrapped back, and it's going out the same way it came, because it came in parallel to row 1 and it's going out parallel to row 1. And you could even prepare a little post-it note of a straight line drawn on it, and now I'll make it a singular integral linear manifold. This straight line is going out parallel to itself. So I'll say that a line in U-trop wraps if it intersects every ray in U-trop except maybe one ray. So in this cubic surface case, this line that comes in, goes out parallel to itself, it misses this one ray, but it's hitting everything else. It's basically wrapping all the way around the origin. I'll count that as wrapping. It's good enough. So yes, we saw that example of the cubic surface. Another example, if DI, if every DI has self-intersection number -2, then there will actually be straight lines that are circles. So try and draw that. So I'm going to be drawing the developing map. So in this case, the image of your developing map, when all of these self-intersection numbers are -2, the image is a half plane. It'll be exactly this half plane. And basically sheets of your developing map, these sheets of UTROP, will just they'll totally fill up this half plane. And if you take a line parallel to the boundary of the half plane, well, if you draw that in UTROP, if you actually draw UTROP as UTROP instead of the universal cover, this line will end up looking like a circle, basically because each of these vectors, we have a vector in UTROP, and then I have that vector repeated on the next sheet. Go the other way and have it repeated eventually. So it hits that vector, and then it goes around and it hits the same, the tip of that same vector again on the next sheet. And so just going around hitting the same point, so it must actually be a circle. Yeah, so that will be a special thing about those cases. This will show up in our classification later. And then if you make things any worse than that, so if all your self-intersection numbers are less than or equal to -2, and at least one of them is strictly less than -2, less than or equal to -3, then not only will the lines wrap infinitely, but they'll actually, they won't trace over themselves and form a circle, they'll actually spiral in towards the origin. So you'll get lines that actually collapse in. And what's happening there is the image of the developing map is no longer a half plane, it's a strictly convex cone. And so any straight line is going to have to hit one of these boundary rays of this convex cone. It might do like this, or maybe it'll have both rays. So with this first line, it'll spiral into the origin like this, or if it hits both rays, it might kind of spiral twice on both ends, and then just self-intersect a whole bunch of times. So in these cases, your straight lines can spiral in on both ends, and you don't get circles. You actually always approach the origin.
Wait, sorry, how is that? How is the last case?
Sorry, say how is what?
The last one, so we do make some identification with a matrix. Which kind of matrix gives rise to this behavior that both sides converge to the origin?
Let's see. So I'm drawing a line which let's see. So the image of my developing map will be bounded by by these two rays that form a convex cone, a strictly convex cone. You can have a straight line which hits both of them, like a line segment which hits both of them.
One side will correspond, one side will converge to infinity, right? Because the matrix has eigenvalue bigger than one and one, and then smaller than one and the other, right?
Yeah, you might be right. Yeah, or I guess I'm not sure now. So what do you think? The monodromy in this case, these two rays here will be there'll be eigenrays or generators for eigenspaces for your monodromy, and one of them will have eigenvalue less real number between 0 and 1. The other will have eigenvalue bigger than 1. So applying the monodromy just kind of takes you further away from one ray and closer to the other ray. See. So I think I still kind of think both ends will spiral in towards the origin.
If you choose a fundamental domain, then like you, the way the two fundamental domains are identified, I think in one side it contracts, and the other side it expands, right?
So I think to go one direction, you multiply by the monodromy, and to go the other, you multiply by the inverse of the monodromy, where your eigenvalues get flipped. So I see. And the rays, the rays or the generators for the rays in UTROP, they're getting further and further out. So relative to the rays, relative to these rays, you're getting very close to the origin. You're getting to these smaller and smaller multiples of the rays. So I think you're spiraling towards the origin on both ends. But even though, your fundamental domain will look like, the generators for it will be bigger and bigger, but our line isn't. Our line is just approaching something that's not getting further away.
Okay, I have to think about it. I had convinced myself that they converge both.
It is possible I'm making a mistake here. It's definitely possible. I should move on.
The behavior on both ends are different. Like the eigen spaces have different, like the eigenvalue associated with each of them have different behavior. So I think like when you take a fundamental domain and glue it to the next one, I think, okay, anyways, maybe we should move on. I'll also think of it.
Don't run out of time. So we can talk more later. So the lattice, so I want to talk about a few more properties of Looijenga interiors that we'll be able to use to help us classify them. So let's let A1 of YZ denote the lattice of curve classes in Y. Curves up to, say, maybe numerical equivalence we can do. And that's that D perp be the sublattice of classes which have zero intersection number, or have intersection number 0 with each boundary component. And then sometimes I'll want to write D perp effective for the sublattice of D perp, which is generated by classes that can be represented by effective curves, not necessarily in Y comma D, but maybe in some deformation of Y comma D. So for example, if I'm blowing up 2 points on here, you could look at E1 and E2, and E1 minus E2 would live in D perp. And in fact, E1 minus E2 actually lives in D perp effective. Just have it up here. It actually lives in D perp effective because I can move this blow up point, or I can move these 2 blow up points around until they coincide and end up at the same point. So I can deform this so that I'm blowing up the same point twice. I blow up this point, and then I blow up this point again, and I end up with 2 exceptional divisors here. And then E1 minus E2 from before ends up corresponding to this divisor now, the exceptional divisor from the first blow up. And so this will be a -2 curve, self-intersection number -2. And this is in D perp, and this time it's effective, an effective curve. Right. So basically, these -2 curves, generically, you won't have any of them. You won't have any effective curves in D-perp, but there are special choices of deformations where they can show up. Now, we can talk about the intersection matrix. Oh, wait, did I? All right, so sorry, there's a bit more I want to say. So the intersection pairing Q on D-perp, we can classify, so that's a quadratic form, or you could say a symmetric bilinear form, however you want to view it. You can classify a quadratic form on a lattice as, say by like a Dinkin diagram. So let me show how to do that. So suppose, let me give another example of this. Suppose that this example will show up soon. Suppose I'm constructing a cubic surface and I take this point and I blow it up twice. So instead of doing 2 non-toric blow ups here, I'll blow up the same point twice. I do the same thing here. And I do the same thing here. So blowing up the same point twice on each of 3 different boundary divisors. And I'm choosing these 3 to be collinear. So because they're collinear, I can take, well, not sure how best to draw it, but I can take a straight line in P2, which hits all 3 of these. And then when I take the proper transform of that line, that will actually hit these 3 -2 curves. And so we'll have, so here's that straight line that goes through all 3 blow up points. I'm going to write a vertex corresponding to that. And then for each of the other -2 curves, I'll draw another vertex. And now if 2 of the -2 curves meet, if they intersect at a point, I'll draw a line between the vertices. Okay, so this long one, that's proper transform of line in P2, that corresponds to the point in the center here. These other 3s from doing the double blowups, they correspond to these 3 points. And you see this is a type D4 Dinkin diagram. So you can contract all 4 of these -2 curves down to a point, and that will be a singular point. So that's a D4 surface singularity. Kind of orbifold singularities and surfaces have this classification by Dinkin diagrams. They're called Duval singularities. And so this would be D4 singularities. The Dinkin diagrams just saying the intersection pattern of these -2 curves that you're contracting. So these will show up in our classification in a bit. We can also, maybe one of the more basic things that right off the bat, Grottek kind of introduces and uses this a lot, is the intersection matrix for the boundary. So say our boundary divisors are D1 through DS. Assume S is greater than or equal to 3. I don't think I actually need that here. And we can look at the intersection matrix, just coming from all the intersections of the DI, DI with DJ for various I and J. This is a symmetric matrix. And we'll say that U or YD is negative definite if H is negative definite. We'll say it's negative semi-definite if H is negative semi-definite, but not negative definite. I could specify this as strictly negative semi-definite to be more clear, I guess. So negative semi-definite, but not negative definite. And then we'll say U is positive if it's not negative definite or negative semi-definite. So it won't be positive definite. It just won't be, it just won't be negative definite or negative semi-definite. So there will be some, there will be some vector which has positive self-pairing with respect to this matrix, with respect to that quadratic form, or that symmetric bilinear form. So the negative definite cases, things don't work as well in those cases. You basically don't have global functions in those cases. So let's see why. So suppose YD is negative definite. So whenever you have a divisor in a surface, such that the such that the intersection matrix built like this is negative definite, you can contract that divisor down to a point. So you can contract D down to a point. It'll be a singular point, a cusp singularity. I think there's a talk later on Looijenga's conjecture, so these will show up there. So we contract D down to a single point, and so U, instead of viewing it as Y minus D, you can work with this contracted thing. So U will be some compact variety minus just 1 point. Singular point, but still just 1 point. And so then you can apply Hartog's theorem or like Serre's S2 condition and say, throwing out a point doesn't mess with your functions at all. It doesn't affect global functions. So we can pretend that we didn't throw away this point because that's not really doing anything. And we can pretend that U is just a compact variety, at least for the purpose of understanding its global functions. And compact varieties, they're only global regular functions are the constant ones. There are no non-constant global regular functions on a compact variety. So yeah, by Hartog's lemma, like I mentioned, code dimension 2 stuff isn't messing anything up. So so we get to this conclusion. The only global regular functions on U are the constant ones. So Gross-Hacking and Kiel, they have this construction of theta functions for the mirror to U, and you can actually identify U with fiber in the mirror. So then they get theta functions on U. But these theta functions, in general, they might be formal Laurent series. They're only defined in some formal neighborhood of some degeneration of U. And if you're in this negative definite case, there's no way you can get away from working in this formal neighborhood, or maybe you could get it to some analytic neighborhood or something, but you can't get it all the way to U because U just doesn't have global regular functions. So you can't get an interesting basis of global regular functions because there just aren't any. All right, so now finally I'm able to go through my classification and tell you, I'm going to have a bunch of statements now of the form the following are equivalent, and I'll have like 7 things or something that are equivalent statements, and we'll view this as some classification of Looijenga interiors. So I'll start with the negative definite cases. So I say the following are equivalent. So first, by definition, we're looking at the cases where the intersection matrix is negative definite cases. So in these cases, the developing map embeds the universal cover of UTROP or UTROP 0 into a strictly convex cone in R2. So we saw this before. This was, I'd said your image looks something like this. You're mapping into some strictly convex cone in R2. You can have a line that hits both segments here. So these are the same as the negative definite cases. In these cases, the monodramy will have trace greater than 2. And as we've sort of mentioned before, one of the eigenvalues will be bigger than 1, and the other will be 1 over that eigenvalue, because monodramy is in SO2Z. So yeah, and that'll add up to something greater than 2. And the 2 eigenspaces will be these 2 spaces generated by the 2 rays. Every line in UTROP is going to wrap infinitely many times, and none of these lines will be circles. And that's, as I mentioned, every line that you draw a pair, any line you draw will have to hit at least one of these boundary rays for this, for the image of this developing map. So then in UTROP, that means that the line has to be spiraling into the origin. The quadratic form Q, those lines. We can look at this quadratic form Q on D perp, the intersection pairing on D perp, and this will be this will not be negative semi-definite. And basically, this is by the Hajj index theorem. Hajj index theorem. So Hajj index theorem says these are projective. You can take some ample divisor that will have a positive self-intersection number. So the direction generated by that divisor in your lattice A1 of YZ, the intersection form will be positive definite on that one-dimensional subspace. And then if you mod out that one-dimensional subspace, then on the remaining lattice, the intersection form will be, on the quotient lattice, it'll be negative definite. So, Q can't be negative, or it can't be negative semi-definite on D perp, because if it's negative semi-definite on D perp and negative definite on D, or on the lattice coming from components of D, then it will be negative semi-definite anywhere, and you won't have this positive direction. And then the converse is a similar argument. Let's see if I'm too mixed up to say, but yeah, both directions basically come from the Hajj index theorem. Let's see, and this next condition I mentioned on the previous slide, you won't have any non-constant global regular functions. And not only does U not have non-constant global regular functions, but its deformations won't either. So see negative semi-definite cases, there will be some special deformations where you do have global regular functions. And then finally, if you, as I also mentioned on the previous slide, you can blow down the entire boundary D to get just a single point, a single cusp singularity. So you get some surface y bar with the cusp singularity. And if D doesn't have any -1 curves, in which case we'll say D is minimal. If D is minimal, no -1 curves, then you have to have DI squared is less than or equal to -2 for all I, and it's strictly less than -2 for some I. And I mentioned that before when I talked about developing maps that look like this. Okay, so these are the negative definite cases. Something else I should say with these, in these cases, you don't get, the theta functions that GHK construct are only defined formally. You don't actually get finite Laurent polynomials, just Laurent series. And you have to work in this formal neighborhood of the large complex structure limit. So yeah, the positive cases, which I'll get to, are where things work much nicer, and you actually get Laurent polynomials and some actual basis for U, functions on U. And so the positive cases will correspond to the, in cluster theory, which is referred to as the full Falk-Gontrov conjecture holding. These would be where it doesn't hold. So next, let's look at the negative semi-definite cases. So these are where H is negative semi-definite, but not negative definite. So that's equivalent to all of the following. So any developing map, delta for U trop 0, that will identify the universal cover with a half plane. So that's this picture I drew before. Universal cover maps to some half plane. So I've mentioned in these cases, this is where DI squared is -2 for every component I, or if D is irreducible, then you have D squared 0. Let's see, and in these cases, I'm skipping ahead a bit. So your monodromy mu in this case has to be conjugate to a matrix of this form. So it's a matrix 1A01. So basically, multiplying by the monodromy will just share your vectors in one direction or the other. You're just sharing parallel to this boundary direction. So yeah, this one. Also, we saw in these cases, you have some straight lines that are actually circles. So all the lines will wrap infinitely. Some of them will spiral into the origin, but you have these special ones where the line is parallel to this limiting line, or these limiting rays, and that will look like a circle. Also, the quadratic form Q on D perp in these cases is negative semi-definite, but not negative definite. So we know that it has to be negative semi-definite because if it wasn't, then by the previous slide, we would be in one of the cases where H is negative definite. But Q can't be negative definite on D perp because then I think the intersection form would be negative semi-definite anywhere, and you'd have a problem with the Hajj index theorem. Let's see. Right, and finally, if D is minimal, so if your boundary divisor is minimal, so you don't have any -1 curves, then you can deform Y comma D to get some Looijenga pair, which has an elliptic fibration. An elliptic fibration with your deformed boundary D prime as a fiber. So let me explain this with an example. So say we have, see I start with P2, and I blow up 3 points on each boundary divisor. So now each boundary divisor will have self-intersection number -2. So this condition satisfied. And so if you choose these 9 blow-up points generically, this will not be an elliptic surface. But so if you choose 8 points, 8 points determine a pencil of cubics. One of the cubics in that pencil is the boundary, these 3 lines. It's a degenerate cubic. And if you take a second cubic, which passes through 8 of these points, that second cubic will hit a 9th point on here. And if we choose that 9th point as our other blow-up point, then you end up with an elliptic surface. If you make that special choice of the 9th point, then this pencil of cubics will, after you do the blow-ups, will become a fibration of your blown-up surface over the base P1 for your pencil, with the fibers being these elliptic curves. One of those fibers is this boundary. So for those special cases, you do have some global regular functions. You have that map to the base of the pencil. But generically, you won't have global regular functions for these. All right, so now on to the positive cases. Low on time. So positive cases, so this slide is basically just the converse to the previous slides. These are where H is not negative semi-definite. The developing map, well, not only does it not map you, the image won't lie in a half space, but in fact, the developing map won't even be injective. So the developing map will wrap all the way around the origin and keep going around. You will fill all of R2 and keep going around. Lines in Utrop, because of that, will only wrap finitely many times. They won't ever spiral towards the origin. The form Q has to be negative definite. The other cases were ruled out on the previous slides. The boundary D supports a D-ample divisor. So by that, I mean a divisor W given by a sum of these DIs, coefficients AI, and integer coefficients AI, such that the intersection of W with any boundary divisor DI is positive. So remember, if your intersection with every divisor is positive, that's enough to be ample. Here I'm just assuming positivity with every boundary divisor. So if you have any effective curves in D perp, those curves will be missed by W. And when you take the corresponding map to projective space coming from this divisor W, those curves will get contracted to points. They'll be contracted to singular points. But if you don't have anything in D perp, if you don't have anything effective in D perp, then this will actually be ample and give you a map to projective space, an embedding of your Looijenga pair in projective space. And the boundary divisor D will be a hyperplane section of that image. So if you take the complement of D, that will be an affine variety. So in these cases, U is affine, or well, maybe not quite affine, because as I said, you could have things in effective curves in D perp that get contracted in this mapped projective space. So in general, U is a minimal resolution for an affine surface. So you take spec of the global sections of U. If U is affine, that spec of the global sections of U is U. But if you have some -2 curves, they'll get contracted when you do this, when you take spec of the global sections. And then U is the resolution of that thing you get by contracting those, the minimal resolution of that singular surface. And so then this spec of global sections of U, this will be an affine surface with the worst of all singularities coming from those contracted -2 curves, those contracted things in D perp. So we see you can view U as a minimal resolution of this affine surface. You can also view it as being deformation equivalent to an affine surface, because generically there are no -2 curves. If you move your blow-up points around, those -2 curves vanish. You don't have to worry about them. And then just to connect to the mirror symmetry stuff and the GHK construction, the theta functions in these cases will actually be finite Laurent polynomials, not these formal infinite Laurent series. So these are the cases where the mirror construction really works very well, and you really get this theta function basis for your ring of global regular functions, and some version at least of the full Fock-Ontroff conjecture holds in the cluster setting. So now I'm going to refine these positive cases even further.
So Travis, I think people are too tired. I think at this point, maybe we should just kind of summarize this kind of course classification before. I think people won't be, I look at them and they are not going to be able to follow. But I think they should be able to take away this kind of 3 cases and how, they're kind of really different from each other.
Okay.
But there's very easy ways, numerical ways of deciding which case you're in.
Okay. So 3 cases being the negative semi-definite. Yes. So these are the important classification is these 3, and then I further refine the positive cases. But yeah, I guess it's maybe we are out of time.
Well, I think if people are interested, then they can look at your slides.
Okay, yeah, I should send you my slides so they can do that. So maybe I'll say very quickly the remaining cases. I break them down into cases where all of the lines in UTROP wrap, some of them wrap, but others don't, and then none of the lines wrap. In the case, the cases where some lines do not wrap, those will be the acyclic cases. The cases where no lines wrap are are the finite type cases, where you only have finitely many torque models. And let's see, a few interesting features that show up. So these are the cases where all lines wrap. So D perp lattice in these cases is a type D or E Dinkin, or corresponds to a type D or E Dinkin diagram. Your monodramy is one of the monodramies that shows up in Kodaira's classification of elliptic surfaces, monodramies of elliptic surfaces. So those monodramy matrices look like these. And all these cases come from taking P2 and blowing up 2 points on one boundary divisor, 2 or 3 points on another, and then either 3, 4, or 5, or however many points on the third boundary divisor. So that's what these are saying. It's how many points are blowing up on boundary of P2. So yeah, those are the all lines wrap cases. Cubic surface is kind of the most basic example of those. And then cases where no lines wrap. So these are the quivers for those cases. You again get Kodaira matrices in these cases. Let's see. Yeah, and they again can come from blowing up P2, blowing up these many points on the boundary divisors. So yeah, I guess I'll stop there. Sending you my slides if you want to look at those in more detail. And yeah, thank you.
Thank you. What's this picture?
Yes, this picture is actually from a different paper. on so this one's on tropical theta functions. So you can do this as images of lines in U-trop for different spaces. So this would be a line which does not wrap. This is a line which wraps and self-intersects once. And then in the case where your intersection matrix Q gives you something of type E7, you can have a line which wraps twice. And then in the, I forget if this is the E6 or E8 case, I think E8, you can have a line which actually wraps, and so self-intersects twice, or wraps around 3 times. So it's just different lines in U-trop in different cases.
I see. Any question here in the room? Or online? Any question online?
Sorry?
Everyone's tired. End of the day here. But thank you very much.
Okay.
Yeah. Thank you very much. Okay, thank you very much.